Okay. Thanks a lot for the invitation, and thanks for putting together this wonderful program, bringing together all these different areas. So my talk will be a continuation of Pedro's talk, so it will be on the superconformal Bootstrap. Unlike Pedro's talk, I'm not aiming for those of you who are experts in the Bootstrap, so you will be very bored, but for non-experts, so I will try to really explain what we want to do, what we can do, what we cannot do, and what our tools are. So please stop me at any point if anything is not clear. So the plan is the following. I will pick up from Pedro's talk. If you recall, we take this abstract viewpoint that the CFT is defined. Is it okay now? Okay. So the CFT, we take it to be defined by a set of local operators and all their correlation functions. So by defining the CFT like so, of course, we are ignoring any type of extended operators like defects. These are interesting observables in their own right, but this is a closed set, and this is what we will focus on. So throughout the talk, I will be talking about trying to solve series, and by solving, I mean this. I consider a CFT to be just the set of all operators and knowing all possible correlation functions. So starting from there, I will tell you what is the Bootstrap approach? So what's the idea? And then I will talk about the recent numerical revival of the numerical Bootstrap program. And for here, I will focus only on conformal symmetry. But then in the end, I will add super in it. So I will tell you what changes for superconformal field series. And here, the organizers asked me to discuss the case of n equals 4 super Yang-Mills. This was not my work, but I will point you to the references when the time comes. So I will take n equals 4 super Yang-Mills as an example of what you can do when you have extra supersymmetry. So, but for now, let me start just with conformal symmetry. And here, I will use the 3D easing as an example, which is also not my work, and I will point you to the references. There are many people who have worked on this. So, what do we really want? The Bootstrap is this old dream that just starting from the symmetries of your problem, the general consistency requirements like associativity and unitarity are powerful enough to completely solve the theory if you're given a few basic spectral assumptions. So this is an old idea, and it was very successful in 2 dimensions for a certain class of 2-dimensional series like the minimal models or rational CFTs, but beyond 2 dimensions and even in 2 dimensions beyond this special type of series, it had not been very successful until the recent revival of Rattazzi, Richkov, Tony, and Vicky in 2008. So this is what I will tell you about now. So the point is that we really just rely on symmetries, and we allow ourselves a few basic assumptions about the spectrum of the theory, but we never need a Lagrangian description. And so the results we get are non-perturbative in nature. We will not be doing any perturbation theory or any such thing, so we don't even need the theories to have a perturbative parameter. So what are our goals? A very ambitious goal would be, can we classify what is the space of all allowed conformal field series, or superconformal field series? So for example, you could ask how many CFTs are there in 3 dimensions with a Z2 symmetry and a Z2 even and a Z2 odd operator. We know of an example, is the Ising model. is this everything? Is there any other series that has this? Or if you now go to supersymmetric field series, we know that maximal supersymmetry in 4 dimensions, you can only have n equals 4 superunion mills. Can there be no exotic series? Is this really the complete list? So this would be a very ambitious goal of the Bootstrap, to just give you a catalog of the conformal field series. And the second goal would be to actually solve specific series. So, and by solve, I mean this. Oh, the critical exponents, I would consider it in solving.
Yeah, but what do you mean by space of, if you don't have Lagrangian description, a space of all allowed conformal field theories?
It would mean something like this: how many operators with one relevant, or how many series with one relevant operator, with 2, with 3, and something building.
So the quantum numbers, that's what you have, I guess.
How many series, how many distinct series, and then I would like to know the critical exponents of each individual series. But just for starters, saying how many, is there another series like the Ising model that is 3-dimensional Z2 symmetry, 1 even, 1 odd? So this is
a set of conformal data, no, that were mentioned the other day, no? The different, the conformal dimensions and
yes.
These parameters, yeah.
And all the, yes, this would allow you to compute all correlation functions, so this is what I will mean by solve. So let me make more precise than now these statements. So by solving a series, I mean knowing all the local operators and all their quantum numbers, the conformal dimension, the spin, plus other quantum numbers the series might have, and then the OP coefficients. So if you recall from Pedro's talk, in a conformal field theory, you have a convergent operator product expansion. So you can replace the product of 2 local operators by an infinite sum over all other operators in the series with some coefficients here. And of course, we want to leverage symmetries as much as possible, so we want to organize our operators in representations of the conformal algebra. So I want this sum to run over conformal primaries. These were the operators Pedro defined. They are the highest weight operators. They are killed by the special conformal transformations. And then you build the whole multiplet by acting with momenta, which is basically acting with derivatives. And we know how to act with derivatives. So if you know how a given primary contributes to the OP, then you automatically know from symmetry how all the descendants contribute. And this is encoded in this function C that Pedro wrote down. So this is just kinematics. This is totally fixed from symmetry, and the only unknowns are these numbers, the OP coefficients, and the range of the sum, what these operators are. And by recursively using this OP, you can reduce any n-point function to 1-point functions, and all 1-point functions are 0 except that of the identity. So if you know this, you know all correlation functions, and this is what we are after. And now the idea of the Bootstrap is that not anything goes. If you just give me a set of operators and a set of these numbers, in general, they will not define a consistent CFT. And so there are strong constraints imposed by associativity of the operator product algebra. So this operator product algebra should be associative. If I take 3 operators, it shouldn't matter which ones I fuse first. And I will be interested in unitary series. So this is another constraint to impose. And so now I finally reached the end point of Pedro's talk, where he showed you that that associativity translates into crossing symmetry. So if you consider a 4-point function, associativity is equivalent to demanding that it shouldn't matter how I decompose it using the OPE. If I take the OPE first of these two guys and these two, or if I do it the other way around. So in a picture, I could take first the OPE with 1 and 2, which I will draw like so. And when I take this OPE, I get an infinite sum over all the other operators in the theory that get exchanged, and then I take 3 and 4. But there was no reason I should have done this like this to begin with, so I could have started by taking the OPE between these two guys in the middle first, which we draw pictorially like so. So 2 and 3, now I take their OPE. I get all the operators in the theory. And then, okay, so this, for associativity to hold, this crossing equation should hold for all possible 4-point functions in your theory. So this is an infinite set of equations for all possible operators you can put here for an infinite set of unknowns, which is this. So in principle, this is a lot of constraints, and you can ask, can we actually solve them? And if we actually were powerful enough to solve them, does it completely fix the theory for you? So let me show you how we go about doing that. First, let me write this in an actual equation and not just pictorially. So for simplicity, I am taking all operators to be scalars and all of the same dimension. So all O have the same dimension, delta O. So now I'm writing Pedro's final equation. So this is just a prefactor that carries the weight of the external operators. It's completely fixed by kinematics, and then I get a sum over all operators that can be exchanged, where these guys, recall, they are conformal primaries. And then I get 2 OP coefficients from the 2 OPs we're doing. And since they're identical, I actually get the number squared. And then a block, the conformal block. So the conformal block is basically, if you're using the OP here, so it's morally this thing squared, it's from the 2 OPs. So this is completely fixed by kinematics, and Pedro showed you how they looked explicitly in 4D. So here, let me just recall you what the cross ratios are that Pedro wrote in his lecture. Okay, so what I wrote there was the first channel, this one. I took the OP of 1 and 2, and then I got this. And now this should be equal to taking the OP of 2 and 3. So now this will look like this. Now I'm taking the OP of 1 and 4, and 2 and 3. And now I get the sum over the operators exchanged here, that I'm calling O tilde of delta L. The OP coefficient squared, and the cross ratios appear exchanged. Okay, so now the idea of the conformal bootstrap is to leverage these equations and try to solve the theories. As I said, this was very successful in 2 dimensions, but beyond that, it wasn't very successful until the recent revival that also came with a change of spirit. So the idea is not, let us try to solve all of these equations, but rather let us try to constrain the space of solutions. So let's make some assumption. Give me a trial CFT. Give me a set of these numbers. Can I prove that that can never satisfy these equations? So that's what we want to do. We are ruling out trial candidate CFTs and not finding them. Yes? The Z2 symmetry. It will not go yet. You will see when it goes, because So for the easing, let's say we consider as the external field the sigma field. This guy is Z2 odd. So in its OP, I'm only going to allow the identity and another Z2 even field, and not itself. So that's where the Z2 symmetry goes in. If there was no Z2 symmetry, sigma itself would be allowed to appear.
Given at least from the field theory point of view, even though there is an Ising transition, there are infinite class of these transitions depending on the fermions present in the theory. For example, there are Ising gross nouveau models with lots of flavors and things like that. And apparently that critical behavior is all different. So are you telling all of this is one CFT or?
I'm saying that you input your symmetries in the theory. So for here I was considering a theory that I was just looking at scalars. And because I had in mind showing you the example of the Ising model, which is a Z2 symmetry, I didn't decorate these guys any further. I will decorate them by saying that I'm thinking about the Z2 odd guy or Z2 even guy. If your guys were charged under some global symmetry, then I should add the global symmetry indices here, and I should deal with this. And you will see this type of symmetry appearing in the supersymmetric case, where you are actually forced to think about, because it's part of the algebra in that case. So the crucial thing to zoom into the Ising model is first to impose that there is this Z2 symmetry, and then to say something about the number of relevant operators. And the most precise determinations from the bootstrap of the critical exponents come when you demand that there is one Z2 even and one Z2 odd relevant operators. Okay. Okay, so as I said, now we will not attempt at solving these equations. We will just show when there can be no solution. So, for example, in this case, can I make some outrageous assumption that I have a theory with a Z2 symmetry? I am looking at an operator that is Z2 odd, and no scalar appears in its OP apart from the identity. So it would be something like this. Can this ever stand a chance of satisfying this equation? And this is something the bootstrap will tell you, no. There is no way you can satisfy this equation unless you add scalars. And actually, not any scalar will go. You will start seeing that the dimension will have to be close to that. Okay, so now let me rewrite that equation a little so it becomes in a form where we can start excluding trial CFTs. So as was clear in the OP I was writing that for the Ising model, if I take the OP between two identical operators, I expect the identity to appear. And then, of course, a bunch of other things, scalars, spinning operators, etc. But the identity should appear, and this choice is a choice of my normalizations. So I normalize all 2-point functions to be 1, which means the identity should appear with coefficient 1. So this is how I define my operators, and then the physics goes into the lambdas. So now, let me rewrite that equation a little. I will pull the identity out of both sums because it appears in both channels. I'm only taking the OP between two identical operators. And it comes with coefficient 1. So I just get a 1 from the identity. And I move it to the other side. And now I get the sum over all operators in the OP 00 that are not the identity. And I get these numbers squared again. This is the conformal. So here I separated the part that is completely fixed by symmetry, the kinematics. So actually, let me call this whole thing f of delta L, and from the unknowns.
I guess that's implicit. But suppose you have two operators which are not the same, but nevertheless the correlation function between the two is non-zero, O1, O2, and the two-point function is non-zero. Then you diagonalize first, I guess.
I will
So what you would do is to take this matrix of OI, OJ, the two-point function, diagonalize it, and then normalize. So your operators are now, by construction, there is no cross terms. OI, OJ will not. Okay.
I'm considering unitary.
That's what I thought, but
So all two-point functions will be positive. So I have a positive definite matrix that I can diagonalize and.
yeah, and there is no
So this is my
cross terms. OI, OJ are zero. Okay.
I have a bunch of operators with the same dimension. I diagonalize them, and then I normalize all two-point functions to
Yes,
one.
I was thinking that.
And their unitarity, of course. Okay, and now, so the idea is, when can this sum rule be satisfied if you give me a trial for the spectrum? So these numbers here, because I have a unitary series and they are a real number squared, this is positive. So what I'm asking is, when can I sum with positive coefficients these things that depend on u and v to get 1? And now I could think of, let's, for example, Taylor expand this equation around point. Let's Taylor expand around z equals z bar equals a half. This is a point where both OPs converge well. It's called the crossing symmetric point. So let me consider Taylor expansion around that. Oh, sorry, yes. I will write it here. Okay, so what are we doing here? If we consider, let's say, so we are summing with positive coefficients these things, so we are spanning a cone where these vectors are f delta L of different operators. And the question is if these vectors can be summed with positive coefficients to give 1. So the question is, where does the 1 vector point? So this is spanning a cone, because the coefficients are positive, and does the 1 stick inside the cone or outside the cone? So this is what we want to show. So I can rule out a trial spectrum if I can show that 1 is actually outside the cone spanned by summing these guys with positive coefficients. So in other words, let me search for a linear functional let me call it psi, such that the linear functional applied on 1 on the left-hand side of the equation is negative, and the linear functional applied on this f delta L is greater or equal to 0 on for all the dimensions in our trial spectrum. Okay, so if I can find such a functional, I will get the contradiction. The functional acting on this side gives me something negative. Then I have positive numbers here, and the functional acting on these guys is positive. So sum of positive terms giving a negative thing is not possible. So this is the game we want to play. We want to make an assumption, let's make an outrageous assumption, and then I try to find a functional that has this behavior. In other words, I try to show that the identity operator lies outside of this cone. Of course, searching over such infinite dimensional space of functionals is very hard. So in practice, what we will do is we will make it finite dimensional. We will consider this basis of functionals, where we basically take derivatives in z and z bar, and we truncate the number of derivatives we take. So at a given order, if I just take 2 derivatives, I'm just considering the Taylor expansion of the crossing equation up to second order. If I can show that even this is not satisfied, then I'm throwing out a trial theory, right? If you give me a trial spectrum and I can show that the second derivative of the crossing equation can never be satisfied, then I ruled it out. So whatever lambda you take, you always will get, if you can find such a functional, you get a true bound. But it might not be optimal, it might be a very boring bound. But as you make lambda bigger and bigger, you get better and better bounds. So now let me show you what type of result this can produce. So now let's go back to the three-dimensional example of a theory with a Z2 symmetry. And considering the OP of Z2, the 4-point function of Z2 odd operators. So this problem, truncated like this, is something that actually can be fed to a computer. So we just plug this data in the computer and it tells us, yes, I can find such a functional, or no, I cannot. So let me consider. So I have the 3D easing in mind for identical operators where sigma is Z2 odd, which means that in SOP, I have the identity, and then itself cannot appear, and then I have some other things. So now let me assume that the first operator that appears in the first scalar operator that appears in the OP, I'm calling it epsilon. Let's assume that delta epsilon is, the dimension of epsilon is a very big number. So let me make a plot. I also don't know the dimension of this external guy, so I will allow myself to vary it. This is its dimension. And for each dimension, I want to make an assumption that the first scalar that appears in the OP of 2 sigmas has a very big dimension. So can I run this machinery in the computer for a given cutoff. Can I find a functional? And yes, I can find a functional, so this point is ruled out. And then I make a less outrageous assumption, and I start going down until the point where I cannot find a functional. And this will give me some curve like this. And as you increase this cutoff, the curve would actually get, the bound will get stronger and stronger. And at some point, you see it converging to some curve like this. So, and all these points that are outside, you found a function like this, so you actually ruled them out. There is no CFT that can live here. But here, I don't know, maybe there is a CFT. And what was surprising is that first there is a special point, there's like a kink in the bound, and that an actual physical theory that we know sits there. This is the 3D easing model. So in this game of just throwing away trial solutions to the crossing equations, we actually stumble upon physical theories. And so this plot that I am drawing comes from this paper here, Elshock, Paulus, Poland, Hitchcock, and Siemens-Duffin. So there is actually a physical theory that saturates it, and this is getting an upper bound on the dimension of the epsilon field on the 3D easing model. But now, actually, people did better than this. This was, keep in mind that to have a consistent CFT, all crossing equations must be satisfied, and this was just looking at just a single 4-point function. So what happens if people put more 4-point functions in the game? And this was done, people considered both the sigma and the epsilon field, so all possible correlations with these two fields. So considering this one, and also the mixed, and of course still imposing a Z2 symmetry, so epsilon is even, and sigma is odd. And now with one further assumption, so I was telling in the beginning, we want to leverage all the symmetries and then a few basic spectral assumptions. So such an assumption is, let's say that there is only one relevant even and one relevant odd. So these are these two guys. So these are the only relevant. So their dimension is less than 3 scalars. And now let's repeat this type of plot. Again, with a slightly modified machinery, because now we need to consider mixed multiple equations. And what people have found is that actually that whole area now becomes a tiny island. So this is excluded. And this little island is allowed. So this is for small delta sigma. There might be some allowed blob for here, for very large dimensions that people haven't considered. But there is this region where there is a single allowed island. And this has led to the most precise determinations of the critical exponents of the 3D Ising model. So if you compare with Monte Carlo, it looks like this is Monte Carlo, and this is actually smaller. It's the Bootstrap. So this is from Kos, Poland, Siemens, Duffin, and Vicky. Okay. So this leaves us very excited that we can actually start not only saying how many series there are with the Z2 symmetry and one relevant and one odd. Well, you see that in this space there is only one that lives inside this little blob, but we're actually starting to get the actual values of the critical exponents. And people can actually, along the boundary of the excluded curve, you can actually get an approximate solution to crossing. So you can actually get more spectrum than just more spectral data than just these two numbers. And this has been pushed for the 3D Ising model. There's a table of operators up to a given spin, various conformal dimensions, that was extracted along this boundary. And so in the final 35 minutes, I will change gears and tell you what happens when you add supersymmetry. Yes. Very crucially, because we are demanding that these numbers are real. So unitarity enters here.
Positivity.
Yes, positivity.
Positivity is where unitarity is entering.
Yes, in Euclidean, it's reflection positivity that enters crucially here in these signs. And also, so what I'm telling you, so we need to give a trial spectrum to play this game. And the trial spectrum is always something like the dimension is greater than the unitarity bounds that Pedro wrote yesterday. So this is for operator with spin different than 0. So we allow for all these dimensions to appear in the spectrum, and then we make an assumption like this one. So we say that delta is greater than delta epsilon for spin 0. So this is the type of trial spectrum that goes into here. So this is one game you could play. You could play different extremization games, right? So now we are doing these exclusion curves, and we chose scalars, but we could have played it with spin 2, spin 4, etc. And it's not clear that these various exclusion curves should be saturated by the same theory or not. So one important question you want to ask is, if you're after a specific theory, what question should you ask the Bootstrap? And that's where we very often input from other methods. So, okay. So now let me show you what will change as we add supersymmetry. So the game is basically the same. Now we want to leverage all symmetry, which is in an even bigger group, so we should feel entitled to stronger constraints. We want to organize our representations, our operators now in representations of this bigger group, so there will be further reshufflings of these guys here to take into account the bigger symmetry. So Okay, so for concreteness, let me focus on 4 dimensions, and let me take the maximally supersymmetric theory, which is n equals 4. So here, what are our generators? Well, yesterday Pedro wrote for you the generator of the conformal group, the momenta. And here, these are the special conformal transformations, and now we want to add fermionic generators. So I'm calling those Q. And we are in n equals 4, so it will be 4 of these supercharges that are spinors. And 4 of the adopted version. Let me be a bit sloppy with placing these. So let me just say a few words about these guys. And there's one more that I will write in a minute. Okay, so just like in the conformal group, you had momenta, and then you had the special conformal transformations, which you can basically think of as an inversion, a translation, and an inversion. So now I'm adding fermionic operators that commute to the momenta, as we've seen in other lectures before. But because of the superconformal symmetry, I'm also getting these 2 conformal supercharges. And they're the analog of K to P's. So these are called conformal supercharges. And then there is an extra thing, because I have 4 of these supercharges, I actually have an SU4 symmetry, which is called an R symmetry. So this is part of the algebra. It appears when I take commutations of these guys. So here, I will then have to decorate the operators with extra indices more than just C2. So now, the questions we want to ask are exactly the same. What is the space of allowed superconformal field series? If you take 4-dimensional n equals 4, then most of us maybe believe we know the answer. It's just n equals 4 super Yang-Mills. And there are good reasons to believe that this is the complete catalog, but the Bootstrap would allow you to explore if there are some exotic series that, for being so exotic, have never been discovered before or considered before. So we believe we just need to specify a simple Lie group, and n equals 4 series come always with the conformal manifold, so with an exactly marginal operator. So this modulo ds duality, we believe this is all there is. So now we can, if this is correct, we can ask, can we solve this series? So what changes if we want to play exactly the same game? Well, for starters, now we have to deal with the SU4R symmetry.
Why this modulo S duality is important?
Oh, because I wanted series up to series that are dual, so that they are just described, they give me the same. Okay, and now we want to, again, organize the operators in representations of the superconformal algebra. So we will need to go from conformal blocks that package together an infinite number of conformal descendants acting with the derivatives. You want to go now to superconformal blocks. So if you start by, if you have a conformal primary, you can now act with these Q charges to get other different conformal families. And you call an operator a superconformal primary if it's annihilated not only by the special conformal transformations as Pedro had, but also by the S, the conformal supercharges. So you want to organize your operators like this. You start with someone who's annihilated by K and S, and then you act with all possible Qs to form your whole multiplet. So this is something we need to take into account when we fix the kinematics. And one other thing that will change is that before, if you remember the sum rule that I just erased, there was a 1 from the identity that we could fix because the identity came with coefficient 1. Now this one will actually be promoted to more. There will be a bigger protected contribution. So there are more operators whose OP coefficients we can actually fix and exclude out from the sum rule. So this is, I will not describe in this talk why this is so, how this happens. This is, actually, in the research talk later the week, I will discuss this type of, why this type of structures arises. But here we will just see it kind of popping up. It seems like there is more that in the end you can fix. The crossing equations are simpler than what you would have thought. And the explanation why this is true, I will talk about later. So now, but if we want to approach this series, what should we do? Here, because the 3D easing model is well known, people thought that starting with the sigma field is a good idea. So what should we do now? Well, there is a guaranteed operator in your conformal theory if it is local, which is the stress tensor. So whatever n equals 4 theory we have, it better have the stress tensor. And why don't we look at that?
These are in the left-hand side of the bootstrap equation?
These will be more terms that I can move to the left-hand side because I can solve for their OP coefficients.
And they do not depend on the theory, particular theory?
They depend in the theory in a simple way. They depend only on the central charge. They do not depend on the exactly marginal coupling. So they are protected. That's why I call them protected. We will briefly see how they arise, but the actual explanation of why this had to be, I will not, this would be a talk in its own. So there is a guaranteed operator, which is the stress tensor. And now I should ask, how does it sit in this bigger structure? So the stress tensor is actually not a superconformal primary. The superprimary is an operator that transforms non-trivially under this SU4R symmetry. So it actually transforms in the 20 prime representation of SU4. And this operator is a scalar, so this is very good because scalars are easier, you don't have to deal with the tensor structures. So this is a scalar of dimension 2. And now, if you act with enough supercharges, at some point you do find the stress tensor. So if the stress tensor is present, this guy also has to be present, so let's consider this one. Now, yes. So yeah, I wrote ... because you need to act several times before you get to the, yes, it sits low in the multiplet. The nice thing about supersymmetry and about this particular multiplet is that generically you should act with all the supercharges in all possible ways and you get a big multiplet. But it could happen that by some conspiracy of quantum numbers, a certain combination of these supercharges actually kills the superconformal primary. In other words, as you start building the multiplet, you find a null state inside. And you should mod out by the null state, and then you get a short-term multiplet. And this is one short-term multiplet. It's actually half PPS. And this gives it some nice features. And one of the things is that, if you recall from Pedro's talk, when you were looking at the 4-point function, he was counting how many conformal invariants he could write on the right-hand side. And he found that it had to be So this was the general structure. And then you have to have an arbitrary function of two conformal invariants U and V. Now you should ask the same question for the supersymmetric case. So how many superconformal invariants are they? And for this particular guy that are half PPS, you find that the answer is again 2. So there's a supersymmetrization of these two guys, and you still have the same number of conformal invariants, which means that I can consider only the superprimary, and I don't have to worry about the descendants. They come for free. So if you give me the 4-point function of this guy, just the superprimary, for free we can get also the stress tensor, just using the superconformal algebra. So now, let me spell out this 4-point function. So now we need to deal with the fact that these guys transform non-trivially in SU2R, SU4R. So when I take the OP of when I take the tensor product of 220 primes, I get a bunch of representations on the right-hand side. So when I take the OP of two operators that transform in the 20 prime, I get a bunch of operators that transform in all those representations. So let me write that. So I'm giving it indices. These are symmetric traceless of indices, and these go from 1 to 6. And let me consider 4 of them. I1. Their dimension is fixed by formal, because it's a short representation. The dimension is fixed to 2. So this should be a 4. And now, if when I take the tensor product of 220 primes of SU4, I get a bunch of representations. Now, I need to sum over all these representations because I will get operators that are exchanged, that are charged under these representations. And now, again, the same function, a function of the two conformal invariants for each of the channels. And something that takes care of the index structure of the SU4R symmetry structure. So these are just some projectors that take these 4 representations and take into account when representation R is exchanged in the OP. So now, each of these guys is what gets an expansion in conformal blocks. So there are 6 representations that appear here. So there will be 6 AR that will obey crossing equations. So they will obey 6 coupled crossing equations. But so far, I only took into account the SU4R symmetry structure and then conformal symmetry. But you should still impose the superconformal invariants. And this was done by Dolan and Osborne. And when you impose superconformal invariants, impose that these 4-point functions behaves as it should, then you find that all AR, all 6 of them, are actually just fixed from one function that I'm calling curly G, that depends on both U and V, and then 3 functions that I'm calling F, that depend only on Z. So recall that U was Z bar. Okay. So actually, you don't have as many functions to determine as you thought you would. You actually have one that depends on everything and one that depends only on z. It's actually a meromorphic function of z, so it's a nice thing to find. And now you want to work out the superconformal blocks, how each representation contributes to each of these guys. So this was done by Dolan and Osborne. And what they found is that this guy, the G, it will get contributions both from generic long multiplets, multiplets that you can act as many times as you want with the supercharges until it stops, and also from these short multiplets that have nulls, and so they became actually shorter, while this F only gets contributions from short operators. So G will have some decomposition now in superblocks, where you have to sum over long with some blocks. And let me not write down what they are. Plus some short operators. While F gets contributions only from short. So recall that short operators, they happen when there's the quantum numbers of the superconformal primary has to be special enough that there is a null state. So their dimensions will actually be fixed in terms of their spin and other R-symmetry quantum numbers. So there are less parameters here. I won't have delta and L, but only some combination, which I'm calling H. And now you work out the crossing equations for these things. You had 6 crossing equations to begin with for these 6 ARs, but there were only these functions. And actually, in the end, you find that, so this is Fi. There were 3 of them. Fi of Z obey a crossing equation on their own. That you can actually solve. So this is, you get this equation and you stare at it, and it actually looks like a 2D crossing equation. And the reason why I will not have time to go into here, but very briefly, there is a way to carve out a 2-dimensional CFT inside in a subsector of n equals 4 super-ring Mills, and this is just capturing this subsector. So in the research talk, we'll discuss this further. But from this experimental point, you're just working out your crossing equations, and you find, wow, this equation is actually very simple. It's a meromorphic function of Z, and it obeys its own crossing equation. I can fix the function by the leading behavior, and I can fix the leading behavior just by the OPE. So actually, we can solve for these guys as they will all be some function of C, the central charge. So this is in n equals 4, the 2 anomaly coefficients C and A are equal. So this is just a 2-point function of the stress tensor. And when I said you can fix these guys from the OP, this is what I meant. When you take the OP, you will find the stress tensor being exchanged. So you know its coefficient, it comes with coefficient C. So you fix it, and you get a function that depends only on C. So this is solved. And from here, you know it had a block decomposition. So you can go on, decompose it in blocks, and read off the OP coefficients of an infinite number of short operators that then you can plug in here. Okay, and now this function of 2 variables, G of U and V, will obey a normal crossing equation, the complicated type that we need to study numerically. But we actually made a lot of progress just by being able to solve for these guys here. So let me write schematically how the equation looks like. So this was work originally by Chris Beam, Leonardo Rastelli, and Balpan Res. Right? So you find some equation like this. So this should remind you of the normal bosonic crossing equation. But now on the right-hand side, I have first F will appear. So F had its own yes. Exactly. So these little f of c are related to the 4-point functions of these vertex operators. So actually, the reason there are 3 is because the chiral algebra of n equals 4 superring mills actually still has some supersymmetry. It's the small n equals 4 in 2 dimensions. And so that's why you have, so there will also be an R symmetry in 2 dimensions, and that's why you have 3 of them. So you could, if you didn't know about crossing, you could fix them completely just from the chiral algebra story with a totally different perspective. But it just falls on you if you write crossing and you see the OP behavior. So now, F will appear here as well in the big crossing equation, but so will the contributions of the short multiplets to curly G that we could read out from here. So this is what I meant when I said the 1 will be replaced with something bigger. There's now an infinite number of OP coefficients, and we have some sort of G fixed of U and V that depends on C. And so this is our handle onto the theory. Everything is fixed up to the anomaly coefficient. Okay. So now, taking this equation, all that I said before in the conformal bootstrap can be applied. We just want to study this numerically. Again, we consider a Taylor expansion around this crossing symmetric point of the equation, and we add more and more terms in this Taylor expansion, and we try to rule out trial spectra. So, okay, I should have said in the beginning what this guy is in n equals 4 superring mills. So it's just the trace, symmetric trace. So, these are the fundamental, the 6 fields of n equals 4. And this is what, so this is what we are considering. And now we want to see what can appear in SOP. So let us look of what, so the protected part was actually fixed. So regarding short operators, we actually know all their OP coefficients and their dimensions exactly. We are done in this case. But now we can ask about long operators and protected operators, whose dimensions we do not know except in coupling expansions or something like that. So let me look at the scalar operator, the first scalar operator that appears in the OP of these 2 guys, that is neutral under our symmetry. So now I will draw a similar plot, but this time recall that the dimension of this operator is fixed to be 2, so I shouldn't vary it, it's actually 2. What I can vary, my handle on the theory will be C. And so the plot that this paper found looks something like this. Okay, this weird point here is not a kink as in the 3D easing model. It's just because somehow the solution of this F short, of this F here, that you plug in there needs to change when you cross this point. Because, so this dot here would be C equal 1/4, which is just U1 n equals 4, so free theory. And this would be the SU2 theory, which has in these conventions 3/4 of central charge. So this is just a change in what our G fixed is, so it's not really a physical kink. So interacting series, they have to have C greater than this. You start with SU2, and then we really don't see what the gauge group is, we just see the central charge. So that's the handle in which theory you are. So, of course, you don't believe that there will be a theory for each C, but if you tune your C to the central charge of SU2, SU3, SU4 superring mills, then you hope that somehow you can reach this theory with this bound. So now the question is, do we think the series actually saturate the bound, or could they, so this is ruled out, right? Or could they live far inside? And also, this series have a exactly marginal coupling, so on which point on the conformal manifold does the series saturate the bound? From large central charge, what they found was that the bound actually matches very nicely with the supergravity results. And so, at least here, it's saturated by a non-theory. You can also check at the free point, and it's also going close to the free results. So then you stand a chance, I mean, you can hope that also along this curve, the curve will be saturated by physical series if you tune your central charge appropriately. So in particular, this number should give you the first operator that appears in the OP of 220 primes that is neutral on SU4R. So it should give you the Konishi. So now the conjecture of this paper is that the curve is actually saturated. Something special has to happen for the curve to be saturated. So it's extremizing the dimension. The whole of n equals 4 superior mules, no matter what coupling you have, all the dimensions should live in here, right? Because this is excluded. So something extremizes this dimension. And a natural conjecture would be that this is one of the two self-dual points of n equals 4. Which one they don't make a claim about, but that it should be one of those. So the claim is that this is actually this will give you the Konishi, which recall is the part of the two fields of n equals 4. At the self-dual point, one of the self-dual points. And what the authors did also with Ashok Sen to go about testing this idea was we do know the Konishi perturbation theory for small coupling. And by S-duality, you also know it for large coupling. So what they tried to do was a resummation in a way that was manifestly S-dual. So a manifestly S-dual resummation of the perturbative results at weak coupling, and then take it to the self-dual point and see if it is consistent with these results. And it actually turns out to, up to this resummation, it seems to be consistent. So this is something that maybe, this type of resummation that maybe can be improved, maybe with the help of resurgent techniques. And so this is still a conjecture. The evidence is pretty much what I outlined, so it would be interesting if lattice results can either confirm or refute this conjecture and tell that some other point is the one that should saturate this bound. Okay, so a few final comments. I was mostly pointing to this value of the central charge, but one could hope that whatever gauge group you take, if you tune yourself to the appropriate central charge, then it's also saturated by the self-dual point on the conformal manifold, and you actually can get dimensions of this here. Okay, so of course, this was just a single correlator. There's still a lot of work that can be done. People have started looking at different correlators of other operators n equals 4 super Young mills, and this could hopefully improve this type of bounds. But recently, there's also been another type of revival of the bootstrap, which is analytic in nature. So it arises, it's completely orthogonal to this numerical line. It arises by considering the 4-point function where two operators become light-like separated. And this type of limit allows you to solve for the large spin spectrum of the theory. And the group here has been very active in doing this. And somehow, in the end, one can actually probe the same type of physics, and a hybrid approach might be interesting. This has been done for the Ising model, combining these two approaches to get dimensions of operators. So this might be interesting possibility. And with that, I end. Thank you.
Any question or comment?
So in planar perturbation theory, Konishi starts at dimension 2 and it goes up.
Yes.
Right? So isn't that bound 2?
This bound here, no, it's not 2. I can tell you the exact number. So the question is what happens to that number.
I'm trying to read it off a plot. It's like 3.175.
Well, actually, I think it goes for, yeah, 2.95.
But the true bound is 2 because in near free field theory, it's 2.
Well,
There's
no,
a lower bound of 2, and this is an upper bound.
Yeah, so you know, you for sure cannot rule out the free point. But the free point, okay, so sorry, I should have put the beginning. So there's a unitarity bound that says that this guy has to be greater than 2 from our representation theory. So this is 2. For sure, 2 is the unitarity bound and it cannot be ruled out. But also, you know, you increase the coupling and you change the value. So wherever there will be an image of the conformal manifold of the, yeah, there will be an image of the conformal manifold that projects onto here. The question is, how does it project? So you should hope, I mean, you should allow more points than just 2 because you should be able to tune the coupling and still get the results. The question is what saturates it.
So just to follow up on that, one thing that's always confused me is you made some statement that Konishi, the anomalous dimension, should fall at very strong coupling because of its sort of S dual, it's dual to the weak coupling result. But is that really clear? I mean, I would have guessed that S duality just means the spectrum of anomalous dimensions has to be reproduced at strong coupling, but is it clear that this particular operator
Sorry, are you talking about this part of the plot here?
Well, if I just go to very strong coupling, you made some statement, which I think is in the Rastelli paper too, that they expect the anomalous dimension of the Konishi to fall again at very strong coupling.
Well, they expect it to be consistent with S duality, yes.
So why does S duality impose a condition on a single operator? I would have said it just says the spectrum of anomalous dimensions at weak and strong coupling should be the same. Is it clear a single operator just crosses over, comes back down again? So there can't be some other operator that drops it and plays the role at strong coupling?
Sorry, there should be no level crossings when you perturb. So you just follow the lowest one around and there should be no kink.
So that's, okay.
Yeah, but that's basically
not a rigorous
genericity in quantum mechanics perturbation theory.
Right.
Otherwise you have extra symmetries that allow for crossings then, and the system is integrable or something like that. We don't expect that.
It was my understanding that in N=4 super Yang mills, there is some higher dimensional operator that I think is the product of actually 220 primes.
The double trace.
Yeah, the double trace is in the same channel, and eventually its scaling dimension is something like 4 minus epsilon, and eventually that becomes the smallest scaling dimension in the channel of the symmetries of the Konishi, and those operators then cross, and the bootstrap would constrain the lowest scaling dimension in that channel, which is no longer the Konishi operator, just as the trace of phi. And then, so that leads me to...
They don't cross, they hybridize. So in condensed matter physics, when two things look like they're going to cross, you get linear combinations of them, and that's what happens. And the linear combination changes. So there's something that goes continuously from one to the other one.
So something like this.
Yes.
So these would be the dimension 4. These would be like the double trace operators, and these would be, this should be 2. These would be the Konishi. And as you tune up the coupling, various things can happen. So it could be that they would cross, so there is no level crossing, and this would be the actual trajectory, and then it should be, here you should have S duality. So that's how the behavior on the other side follows from this one. And here actually it would tell you that if this is the case, if there would be a level crossing and then there is not, then it would actually tell you that the maximum might not be at the, so the question here, so what the bootstrap is trying to bound is the dimension of this guy, the lowest guy in the theory. So the question is, when does the lowest guy attain a maximum? Is it at the self-dual point or is it in another point? And in this case, it could actually be, if this picture is correct, if there would be almost level crossing, then this shouldn't be the self-dual point, it could be a point below. If not, it could be, the bound would just look like this guy goes around in a symmetric way, and I don't know how this goes around, and because it should be symmetric, it could attain a maximum at the self-dual point.
Well, I guess as far as the bootstrap is concerned, so they're just looking at the lightest operator. So even if it, if it does cross, I mean, the Konishi operator is the light operator, right? Even, I mean, there's no other definition of that operator at strong coupling from this point of view. It is just the operator which is, I mean, so I mean, what this method does is that it bounds the lowest operator, right? Lowest non-supersymmetric operator of a certain symmetry. So whatever is the lightest operator there, we are putting a bound on that. So
as long as the trace phi squared overlaps the lowest operator, we would see it. So it doesn't matter in that sense what you want to call it, right?
Yeah, from the bootstrap, it's the lowest operator you find in your spectrum, and the question is, at which point in the conformal manifold does it attain its maximum value? If it's the self-dual point or not.
or comment? If not, let's thank the speaker again.